This lesson is related rates. We will be dividing this lesson into three parts. The first part, we will explain what we mean by related rates. The second part, we will work some examples applying related rates to those examples, and then we'll do some what are known as traditionally word problems, which involve the technique of related rates. So our goal is to take an equation in terms of x and y, and we need to incorporate t, which is time, into the equation. That's our task. We have an equation in terms of x and y, and we need t, and there is no t in the equation. Now, before we begin, let's remember the premise we're going to be working on is the fact that time hums in the background of everything you do. Think about this fact. Time is a part of everything you do. Now, until now, we've been interested in changing y as x changes. That's your dy dx. Now we're interested in changing x and changing y as t changes, that is, time changes. So we're interested in dx dt, changing x per change in time, and dy dt, changing y, change in time. That's what we're interested in. Let's take a situation. We have y is equal to x cubed. We're told that the equation is y equals x cubed. That's the path of the graph, and that the x coordinate is changing 2 units per second. In other words, dx dt is 2 units per second. We have a table here. We're calling it table 1. We have 3 rows here. This is time, starting at time 0, cut it off at 10. Now, x is changing at 2 units per second. So when you start out at 0, in 1 second, you go 2 units to 2. In another second, you go to 4. Another second, you go to 6, and so on. Now, the change in x per change in time we were given, that's 2. It's uniformly, consistently, always 2. So that's how that table is constructed. Now we have example 2, or table 2, excuse me. In table 2 consists of table 1 with 2 additional rows, these 2. So this is nothing more than table 1 from the last slide. Now, let's see how we get these values for y. Well, t is 1, x is 2. Now remember, y is x cubed. So if x is 2, then 2 cubed is 8. When x is 4, then 4 cubed is 64. When x is 6, 6 cubed is 216, and so on. So that's where we get those y values from applying this given function to it. Now, then we have here dy dt, and you see these numbers, 24, 96, 216, 384. Where are we getting those numbers? How do we come about arriving at those numbers? And that's the task in front of us. In other words, how do you find dy dt? So let's see. Let's start out by saying we're given dx dt. Now, what does the fact that we have dx dt means that x must be a function of t. So we're going to write x is a function of t, call it f of t. What is it we're looking for? We're looking for the values for dy dt. Well, in order to find dy dt, that means that y is a function of t also. So we'll write y as g of t. Now, we've constructed an expression here. It's a fairly simple expression. If it was too simple, it wouldn't get done what we want, but if we don't want to make it any more difficult than we have to. In other words, we've included no trig functions, no products, no quotients, no exponentials, no logarithms, just x squared plus y cubed is x to the 4th plus y squared. And remember, in our problem, we're given dx dt, we want to find dy dt. So the same is true here. We want to take this expression, given the fact that we're given dx dt, how would you find dy dt? So now, dx dt, we said, implies that x is a function of t. And dy dt implies that y is a function of t, y is g of t, x is f of t. So what we're going to do is take our given expression here, and everywhere there's an x, let's put its equal f of t in. We've done that here and here. And everywhere there's a y, let's put g of t. So we do that. So now we're going to take the derivative, remembering to use the chain rule. You say derivative of what? Derivative of this. Now the derivative of this is going to be 2 times f of t, using the power rule. Chain rule says you have to take the derivative of what's inside parentheses. That's f prime of t. So this will be 2 f of t, f prime of t, which is what we have here. This, on the other hand, is going to be 3 g of t squared times the derivative of g of t, which is g prime of t. So it's 3 g of t squared, g prime of t. The next expression is f of t to the 4th power. So that's going to be 4 f of t cubed, derivative of f of t, f prime of t. And lastly, we had g of t squared. Its derivative could be 2 g of t first power times derivative of what's inside parentheses is g prime of t. So that's what we've done there. We've taken the derivative and applied the chain rule, using the chain rule and the power rule. That's all we've used is the power rule. Now, if x is a function of t, then f prime of t must be dx dt, or dx dt is f prime of t. And likewise, if y is g of t, then dy dt must be g prime of t, or vice versa. So what we're going to do now is, this is just a recopy of our expression after taking the derivative from the previous page. And what we're going to do now is, everywhere there's an f of t, we're going to put an x. And everywhere there's an f prime of t, we're going to put a dx dt. And everywhere there's a g prime of t, we're going to put a y. And everywhere there is a g prime of t, we're going to put a dy dt. So look, we have 2x dx dt, 3y squared dy dt, 4x cubed dx dt, and 2y dy dt. So that's all we've done there. But now we have what we want. We've taken our original expression, which was just x's and y's. We've played around with it, and now we've got it back in terms of just x's and y's. And in addition, we've put in dx dt and dy dt's. And why is this good? Because remember, we're given dx dt. We want dy dt, so we're well on our way to getting what we want. However, this involved a little bit of work. We started here, slide 1, slide 2, slide 3, slide 4 to get to the desired results. Let's see if we can do this without so much labor. Let's go back to our original expression that we created. X squared plus y cubed is x to the 4th plus y squared. And what we're going to do is, we're going to play off of what we did with implicit differentiation in a way. Stay with me on this. Derivative of x squared is 2x. Put a dx dt with it because it's an x term. Derivative of y cubed is 3y squared. Since it's a y term, put a dy dt with it. Derivative of x to the 4th is 4x cubed. That's an x term, put a dx dt with it. Derivative of y squared is 2y. That's a y term, put a dy dt with it. Now compare this with this from the previous slide. And this is the result of 4 pages of work, 4 slides. This is done in 2 lines here. So we now have a way to do this. Now, some might say, well, why didn't you just give us this to start with? We had to discover this. We did not. This came as a result of looking at our work and seeing a pattern. We could not see a pattern in the earlier work where we listed them. So we had to have, first of all, we had to do that work to come up with this shortcut rule. And this is not the first time we've come up with a shortcut menu. And it's always been the result of doing a lot of work and then finding a simpler way of doing it. So what we'll be doing now, from now on in this lecture, is when we want to find dx dt and y dt, we're just going to do it quickly as we have here. Let's, again, derivative of x squared is 2x dx dt. Y cubed is 3y squared dy dt. X to the fourth is 4x cubed dx dt. Y squared, 2y dy dt. Make sure you understand that. Now, before we go and work some examples, let's go return to our original problem, which is y equals x cubed, and we're given dx dt, and see if we can figure out how we filled in that table. So y equals x cubed. So let's apply a menu. Derivative of y is 1, put a dy dt with it. Derivative of x cubed is 3x squared, put a dx dt with it. Okay, got that? Now we're told that dx dt is 2 units per second. So we'll substitute in for dx dt 2. And so dy dt becomes 3 times x squared times 2, or 6x squared. Back to our table. The only difference here is we've inserted this information that we did not have before, and that is dy dt is always 6x squared. Now let's see. X is 2. Square 2, you get 4 times 6, 24. X is 4. Square 4, get 16. 16 times 6, 96. X is 6. Square 6, you get 36. 6 times 36 is 216. And that is how we got those values. Okay. So now we're ready to go to part 2 of this lesson, and that is, let's look at some examples. Now, a lot of books don't give you examples. They skip this and go right into word problems. We're choosing to do examples first so that you can pick up the pattern of what we're doing. Word problems in themselves are hard enough. You need to have the pattern down and then go to the word problems, or at least that's the premise we're working from in this lecture. So let's look at example 1. Y is x squared and dx dt is 2. That's our given. And find dy dt when x is 3. So let's begin. Menu. Derivative of y is 1. Put a dy dt with it. Derivative of x squared is 2x. Put a dx dt with it. Now we want dy dt when x is 3. So we'll put in 3 for x. And we're told the dx dt is 2. We get 12 for our answer. Now, we're not putting in any units here. We haven't given you any units, so the answer won't have any units. When we get to word problems, we will introduce units, but not now. We will have no units associated with this. Now notice, this answer is 12 at 3, but if I put in, say, 5, this answer becomes 2 times 5 times 2, okay? So this is the answer you get when x is 3. You get a different answer when x is 5 or whatever. Keep that in mind. Example 2, y is x cubed minus 2x squared, dx dt is 4, find dy dt when x is 5. Again, derivative of y is 1, dy dt. This will be 3x squared dx dt and minus 4x dx dt. Both of these have a dx dt, so we're electing to pull the dx dt out and simply write it as 3x squared dx dt and negative 4x dx dt. Do you have to do this? And the answer is no. We're choosing to do this because we somewhat believe in simplifying if it's simple and easy enough to do as we go along. I would do the same thing if we had an answer of 3/12. I'd call it 1/4. So we're working something in arithmetic. But anyway, you'll get the answer if you don't, same answer if you don't do that by putting that outside. Now, let's get our answer. We're told that y, when x is 5, so let's put in 5. It was an x, so we put in 5 and a 5 here. And now dx dt is 4, and we substitute in, and there is our answer. Example 3. Y is x cubed plus x, dy dt is 26. Find dx dt when x is 2. Now you may be looking at this and saying, isn't this more or less the same thing we did in example 2? And if so, why are we doing another one? Let's reread the problem. Y is x cubed plus x, and dy dt is 26. Now, did you read that as dx dt is 26 and find dy dt? If you did, then that's why you think it's the same problem, but it's not the same problem. This time we're giving you dy dt, and we're asking you to find dx dt. The reason we're working this example is because we want to instill in your mind, again, as often as possible, read carefully. So work this problem. Derivative of y is 1, dy dt. Derivative of this is 3x squared dx dt. This is 1 dx dt. We pull the dx dt out. Now we're ready. Substitute for dy dt 26 and substitute in for x 2. Do the arithmetic, and we get 26 is 13 dx dt. So dx dt is 2, and that is your answer. Now, if you had read it incorrectly and assumed that this was dx dt and we were looking for dy dt, you would have gotten an answer, but it would be wrong because you didn't find the answer to what was asked. You found some kind of answer, but it's meaningless based on what we were given. So read carefully. Read carefully. Example 4, we're given x squared plus y squared is 25. Dx dt is -3. Dy dt is what we want to find at the point -3, 4. In other words, that's more or less saying x is -3 and y is 4 and 4. In fact, that's what it is saying. When x is -3 and y is 4, that's an ordered pair. Now, just as an aside, a note, x squared plus y squared, for your information, equals 25 as a circle whose center is at the origin, that is 0, 0, whose radius is 5. Do you need to know that to work this problem? No, you do not. We simply supply that information to give you an idea of we're working on a point moving around on a circle. So let's begin. Derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt equals 0. We have another opportunity to simplify work. That is, we can divide everything by 2. So we are. Do you have to? No. But we are doing that. Now let's put in what we know. We know x is -3. So for x, we're going to put in -3. And then for dx dt, we're going to put -3. And for y, we're going to put in 4. And then we have dy dt, which is what we want. And then we solve for dy dt, and we get dy dt is -9/4. Now don't let the fact that dy dt is negative, nor that dx dt is negative, don't let that bother you. We're not going to truly show you through this example what's going on here, what this answer means, except we will indicate to you that when you have a dy dt or whatever that's negative, that means usually one of two things. It means it gives you the direction in which you're moving. If it be on the number line, it would be x would be moving to the left and positive be moving to the right. If it's on the y-axis, it's moving up would be positive and down would be negative. Or it can mean something, if it be like radius or something, it means it's increasing if it's negative, increasing if it's positive and decreasing if it's negative. But don't worry about that now. But we want you to realize this is no problem. Just go with the problem and give the answers a proper sign that it's entitled to based on the work you have. So that's example 4. So that's 4 examples. Hopefully now you've got the rhythm of the menu, how you do that. And now we'd like to work some word problems. And in word problems, we have to come up with the equation ourselves. It's not given to us. So let's start by example 5. It says the radius r of a circle is changing at the rate of 5 inches per minute. That is, dr dt is 5 inches per minute. How fast is the area changing when the radius is 10 inches? In other words, we want to find dA dt, area per change in time. So we're lucky enough that we hopefully know an expression for a circle that involves area and radius. That's area is pi r squared. we take the derivative now, just like the derivative of y is 1 dy dt, the derivative of a is 1 dA dt. And the derivative of pi r squared is 2 pi r dr dt. And we're given dr dt is 5 inches per minute. So we'll substitute in the place of dr dt 5 inches per minute. We're told we want when the radius is 10 inches. So we substitute in 10 inches for the radius. And then we just simply multiply this out and we get 100 pi. And we realize this is inches times inches is inches squared divided by minutes. Now, let's go to the note here. We're not going to put the units into the problem as we go along because it kind of muddies the situation. We're just going to use the fact that area is square units. Linear, like if it's changing radius, radius is linear, so that would be just inches. Area square inches. If it were volume, it would be cubic inches. So we're going to supply wait until the end, and we're going to reason out what the units should be based on what we were given and what we're looking for. In this case, it's area, it's square inches. Why is it inches? Because we were told inches. Why minutes? Because we were given the problem in terms of minutes. So just to caution you, now, you need to check with your instructor or your textbook or whatever before you begin to do that. Your instructor may say that the units have to appear throughout the problem, and if that's so, it's no real problem. You just put them in. In fact, it'll be a good check because you'll know, hey, well, it's came out square inches. Well, this area should be square inches, okay? And so keep that in mind. We will be putting the units in at the end of our problem, but we will explain why they are what they are. We have the height of a cone is always twice its radius. That's we're given. The height is always twice its radius. The volume is changing at the rate of 64 pi cubic feet per minute. How fast is the radius changing when the radius is 2 feet? So first of all, you need to know or locate the formula for the volume of a cone. And that's what you have here. The volume of a cone is 1/3 pi r squared h. Now, before we go any further, we're in single variable calculus. We're in calculus 1. We've got too many variables here. We've got v, we've got r, we've got h. Too many different variables. However, we are told in the beginning of the problem that the height, the h, is twice its radius. So height is twice its radius. So what we're going to do is we're going to substitute 2r in for h. Now we'll just simply multiply this out and we get 2/3 pi r cubed. Now we'll take the derivative, dv dt is, derivative of this is going to give us 2 pi r squared after we cancel and everything, dr dt. Now in the place of dv dt, we're going to put 64 pi. Okay, and in the place of r, we're going to put 2. And we're not putting the units. We're not putting in 2 feet. We're not putting in cubic feet per minute. You can, but we're not going to. Now, so that's all we do is we put 64 pi in for the volume, and we put 2 in for the radius, and now we do the arithmetic, and we simplify, and we get dr dt is 8. Now, this is, radius is linear. We're in feet, so this is going to be feet, and the time is minutes, so it's 8 feet per minute. So that's our answer, okay? We explained that the units are feet per minute because radius is a linear measure, first degree, okay? Now let's look at example 7. We're given a triangle. The hypotenuse of a right triangle is 13 centimeters. The base, we're calling B, is changing at the rate of 8 centimeters per minute. And that is dB dt is 8 centimeters per minute. Now, we have an A part to this problem. How fast is the height dHdt changing when the base B is 5 centimeters. So we need a relationship that involves base and height, and that's the Pythagorean theorem, which says that h squared plus b squared is 13 squared. That's what we've written here, and 13 squared is 169. Now, we want dHdt. We want dHdt. Now, down here we've written, we're given b is 5 centimeters, and we're given dBdt is 8. That's from the previous page. We've just rewritten here so we don't have to go back. So let's take the derivative. We get 2h dHdt plus 2b dBdt, and the derivative of 169, of course, is 0. And we're going to take the liberty to divide everything by 2 and write it like this. Now we are going to need we need dHdt. We know dBdt, we're given that. We know b, we're given that. We don't know h, so we've got to, how are we going to find h? Well, we're going to come up here and use this expression, and which says that h squared plus 5 squared, well, b is 5, is 169. So h squared is going to be 169 minus 25, 144. And so h is the square root of 144 is 12. So now we know everything we know. We know h, we know b, we know dBdt, so we substitute those in and we solve for dHdt, and we get minus 10/3. And this is going to be centimeters, and height is centimeters, it's linear. And the time is minutes, so it's going to be minutes. And there's our answer. And this simply means that the height is decreasing as the base is increasing, okay? And that's all that means. Now, this problem has a B part. It asks you how fast the area of the triangle is changing. Well, you need a formula for area. Well, area is 1/2 base times height, okay? 1/2 base times height. Now, we're going to use, we want to find dAdt, so we're going to take the derivative. We're going to have to use the product rule here. So I pull the dAdt, pull the 1/2 out. That's the first. B times derivative h, that's 1. Put a dHdt with it, plus h times the derivative of dBdt, okay? Since the derivative of b is 1, that's dBdt. So now we have everything we need, okay? We know b, we're given that, we carry that over. We know dBdt, okay? We know dHdt now because we just found it in part A, okay? This is from part A. And so, and we know what h is because we found that to be 12 from part A. So we've got everything we need. We've listed it down here so we don't have to go back to part A. We're given this in the problem. We found this in part A. We found this in part A. And so we have everything we need. And so we simply substitute in and we get an answer of 119/3. This is area, it's square centimeters per minute. Now, the downside of this problem here is, if it were like a test problem, is if you gave this problem and you missed the A part, you're going to miss the B part because you need the result of the A part here to do the B part. So maybe this is not a great test problem. We're not saying it wouldn't be given. We're just saying it's has some downside to it. There is a way to construct a problem where you want to find the area and you don't have to you don't have to have the problem. It's not dependent on the A part of the problem, but that's the case that we have here. I just wanted to make that notice aside. But what we're trying to show you here is you've got to use the product rule. So we work through these problems, not necessarily make the problems easy. Remember, word problems are hard, but this one's a little harder because you have to use the product rule. Let's go to the C part. And we want to know, given what we know in part A and part B, how fast is the angle changing? And what's the angle? That's this angle, this acute angle right here. In other words, as B is growing and whatever, how fast is the angle change? So we need a relationship that involves, what we want is d theta dt. So we need a relationship that involves the angle theta. So we're going to have to bring trigonometry into this. We're going to use the sine function. The sine of theta, remember the sine is the opposite side over the hypotenuse. So it's h over 13. We've listed that here. You don't have to use the sine function. You could use other trig functions to do this problem. We have chosen to use the sine, and we're not going to explore this problem with all the others you might want to on your own. So this is our relationship. And remember, we need dHdt. So here's what we're going to have to do. We're going to take the inverse sine of each side of this equation. Why are we doing that? Well, the inverse sine of the sine of theta is theta. The inverse sine of the sine of theta is theta, and then we have the inverse sine of h over 13. So let's take the derivative of theta is 1. Put a d theta dt with it. The derivative of the inverse sine of h over 13 is the derivative of h over 13, which is 1/13 dh dt over 1 minus the square root of 1 minus this quantity squared. You'd have to recall your derivative of the inverse sine formula to work this problem. Okay, so you have to have had the derivative. So we're not saying that when you're working these problems that maybe you haven't had the derivative of the inverse sine, but you are interested in related rates. So you would have to pass on this part of the problem. We're working this problem because it's there for us for the taking. This is an interesting problem, and so we will stay with this. And now, believe it or not, we are where we want to be. In other words, dHdt is 1 over the square root of 1 minus h squared over 169 times 1/13 dHdt. Now, we're given dHdt. We got that from part 1. We've listed that here. We've got h from part 1. That's 12. We've got this here. So we're all ready to do this problem. We just simply substitute in and we do the arithmetic here. Okay. We'll leave it for you to go through this and verify it. And our answer is minus 2/3. Now, angle measurement in trigonometry is, unless you're told otherwise, radians. So this is minus 2/3 radians. Time is minutes, so radians per minute. And that means the angle is getting smaller as the base grows. Okay. And that's all that means. So this is probably a multifaceted problem. And if you have not had some of the calculus necessary to work on it, don't throw the lecture out simply because you haven't had inverse trig formulas yet or whatever. Okay. Let's move to the next problem. Example 8. Find the volume of a sphere is increasing at the rate of 10,125 pi cubic inches per minute. How fast is the radius changing when the radius is 15 inches? So we need this formula, which is the volume of a sphere. A volume of a sphere is 4/3 pi r cubed. If you're not familiar with that, you would need to look that up. Okay. And now this is pretty straightforward problem. Derivative of v is 1 dv dt. The derivative of this, you take the derivative 4/3 pi, and you have a 3r squared, and you cancel, so you get 4 pi r squared dr dt. Now you simply substitute in for your dv dt is this as given, okay? And you substitute in for r, the 15 that you're given. What is it you want? You want to find the dr dt, so you simply substitute in, you do the arithmetic, and you get this, which happens to reduce to 45/4 inches per minute. This is actually, as far as what you do here, is a fairly simple problem. The previous problem, number 7, is probably the most tedious problem in this particular lecture. So this one is pretty straightforward. We're trying to show you need to know your formulas from geometry or have access to your formulas. Let's say that. If you don't know them, you need to look them up if you're allowed to do that. Again, you need to check with the expectations of your instructor and your course. Let's look at example 9. The edge, which we're calling E of a cube, is increasing at the rate of 3 inches per minute. That means dE dt is 3 inches per minute. Here we have a cube. A cube is all the faces are squares, so it's E by E by E. E by E by E. Depth is E, height is E, width is E. And we have 2 problems here. We want to find the rate at which the volume of the cube is changing when E is 10 inches. So what's the volume of a cube? Sides cubed, E cubed. So dV dt is 3E squared, dE dt. We want dV dt when E is 10, and we're told that dE dt is 3. So we do the arithmetic, and we end up with 900 cubic inches. Remember, this is volume, so it's cubic inches per minute. The B part, we want to find the rate at which the surface area. Well, a cube has 6 surfaces, and they're all squares. So the area of each surface is E squared, and there's 6 of these. Hence, this is the formula for surface area of a cube, 6E squared. And we want ds dt. So ds dt is 12E dE dt. And now we simply put in for 10 is the same 10 inches here. And the ds dt is the same 3. dE dt is the same 3. And so we do the arithmetic. We come up with 360. Surface area square inches per minute. And you're done with this particular problem. And now we come to example 10, which is the last exercise we're going to look at. What we have here is, for those of you that are familiar with baseball, this is a picture courtesy of another book. We've lifted this from of a baseball diamond. And we have a player, a runner on first base. We have a runner on second base. The distance between bases is 90 feet. We have a batter, not shown here. The batter hits the ball, and the runners start running. One from first starts running towards second, and then one from second runs towards third. Now we're given this piece of information. The moment the ball is hit, the runner at first base runs to second. That runner, he or she is going at 18 feet per second, and the one leaving second base is running at 20 feet per second. So here we have taken this, and we have a drawing here. Now this is what's happening. So at the end of 1 second, base runner 1 has gone this far, okay? There's this much further to go. It's gone X, the whole distance is 90, so this is 90 minus X. The runner from second base goes Y distance. So this part of the triangle is Y, and this part of the triangle is 90 minus X. What is it we want to find the rate at which the distance between the 2 runners is at any time? In this case, after 1 second. So this is what we're interested in, dD dt. We're interested in dD dt. D is the hypotenuse of this right triangle. So let's get an equation. Well, the equation will be D squared is 90 minus X squared plus Y squared. Okay. Now, derivative of D squared is 2D dt. Derivative of this is 2 times 90 minus X to the first power times the derivative of what's inside, which is -1, giving us a -2 here. Dx dt, derivative of Y squared is 2Y dy dt. Okay, since we have 2's everywhere, let's get rid of the 2's by dividing everything by 2. You don't have to do this, but we've chosen to do this. Okay, so that's our equation with the derivative, and we need to find d dt. So we need x, we need y, we need dx dt, we need dy dt. Now we're given dy dt, that's 20. We're given dx dt, that's 18. And we're told that we're interested in it after 1 second. So after 1 second, this runner has gone, the one's going 18 feet per second has gone 18 feet, and the one's going 20 feet per second, nicely, has gone 20 feet. So this is basically a summary of what we just talked about here. In other words, what we have here, we know when t is 1 second, x is 18 feet, since he's going 18 feet per second, and y is 20 feet, since he's running 20 feet per second. So we have those two numbers, but one thing we don't have is what d is. So we're going to have to find d by going to our expression, our Pythagorean theorem, and plugging in for x 18 and in for y 20, and do the arithmetic, and we come up with this answer, which is not so nice. We combine it, still not so nice. Still, this is about as nice as we can get it. So we have that d is 4 times the square root of 349. Dx dt is 18 feet. Dy dt is 20 feet. X is 18 feet. Y is 20 feet. So we come over here, and what we're going to do, this is our expression for what we have, after we divide it by 2. So what we're going to do, and this is what we know from the previous page, we know that d is 4 times the square root of 349, that x is 18, that y is 20, dx dt is 18, dy dt is 20. So we substitute in this value for d, okay? And we substitute in 18 for x, and we substitute 18 for dx dt, and we substitute in for y, we substitute in 20, and we substitute in for dy dt, also 20. And now we simply do the arithmetic, and we get this, which simplifies to this, which is approximately negative 11.99. And this is feet. The distance is feet. Time is second. This is, might as well say, for all intents and purposes, it's negative 12 feet per second, but we'll leave it to show you that it's not an exact number. The negative sign simply means that it indicates the distance between the two runners is decreasing. Now, before we leave this lesson, remember, word problems are not simple for anybody. Some of these were not bad, and we wanted some of them not to be bad. Some of them were more difficult than others. We wanted some that were more difficult. This whole lecture series is set up to appeal to people who want to be acquainted, but there's a bailing out point where they feel like they are successful. Others think that these are really too easy. Are there any more challenging problems? So we've tried to give you a mixture here of the word problems, but keep in mind, the first part of this lesson was technique, how to find work dy dt and dx dt in the equation. That was theory. Part you want to concentrate on is the middle part. That's where you were given examples and you were asked to find dx dt when given dy dt or vice versa. You want to concentrate on that. And then you want to look at some of the early word problems in the third part, realizing that a couple of the problems, and we've tried to be honest with you, they're harder than others. And so before you get too worried about what your knowledge is, think of what ones you were able to do, and then see if you can concentrate on maybe developing some mastery of the harder problems. But at any rate, this is an interesting, hopefully, lesson for you on related rate technique. And this concludes this lesson.